Hello students, this is the module 2 of the class, Distances and Brightness. The learning objectives for this module, the invisible third dimension in the sky, which is the depth, and how we measure it. The distance ladder in its first step, the parallax, familiarity with combining magnitudes, and a notion of stellar motions, true and apparent. As we mentioned in the previous chapter, the objects in the sky are so distant from Earth that we lose the notion of depth, and all the objects are encrusted in a dome, the celestial sphere. That begs the question of how do we measure the distances from objects to the Earth? How far is the moon and how far is the sun? How far are the planets? How far are the stars and the other objects on the night sky? Answering this question is by no means trivial and has motivated astronomers throughout millennia. The effort led to several methods for estimating distances, leading to what we call the distance ladder. In this chapter, we will study the first step in the ladder, which is the parallax. The reason why we know the distances to the stars is the parallax. So parallax is the shifting position of a fixed object relative to a distant background when viewed from different points. As you can see here from this figure, you have here that an object is at this point O, and you have two different observers here, observer A and observer B. Observer A is seeing this object projected at this distance, and observer B is seeing the same object projected at this distance. The angular distance between these two objects is called the parallax. So this is a way that we could measure the distance to the moon. This is triangulation. If you are at a position on Earth and have a baseline, say another position on Earth, and you measure the position of the moon relative to the stars, by measuring the shifting angle, you would be able to measure the distance to the moon. You have a triangle here that you can work out the trigonometry, a plane, a triangle, and find out the distance to the moon. This is an example of this parallactic shift of the moon. This is the moon seen at the same time from two different locations, one in Kansas and the other one in Maryland. You can clearly see here the shift with respect to these stars that are fixed in the frame. So this method to find the distance to the moon was done in antiquity. Hipparchus could determine the distance to the moon to about 60 Earth radii by using the concept of parallax. He knew that there was a total eclipse of the moon in the Hellespont, which is in the modern day Strait of Dardanelles. And he got word that the same eclipse was only partial in Alexandria, with the moon covering about 4/5 of the sun. So this is what was happening. Here is the eclipse as was seen from the Hellespont. And here is the vision from Alexandria. So he knew that the disk of the sun has a diameter of 30 minutes. So from Alexandria, the limb of the moon was 6 minutes away from its position seen from the Hellespont, right? There's this 30 minutes, 4/5 of the sun was covered, there was 1/5 left. So 6 minutes away from its position seen from the Hellespont. Hipparchus also knew that Alexandria and the Hellesponts were 9 degrees of latitude away in an almost exact north-south line, meaning that they were the same longitude. So from plane trigonometry, the baseline would be d, where d is the distance from the two cities, is equal to the radius times the angle. Because this angle is very small here, the sine of the angle is approximately the same. So r is the distance to the moon, and alpha is the parallax angle. You would have r is the distance between the cities over the angle. It gives you about 90 Earth radii. The actual value is 60 Earth radii, so Hipparchus got very close, within a factor of 2. The distance to the sun was measured also due to a method of parallax. Similar to the parallax of the moon, used to measure the distance to the moon in an eclipse, the transit of Venus was used to measure the distance to the sun. The distances within the solar system were not really known, apart from the distance to the moon, until this measurement of the parallax of Venus. So you see here two positions on Earth, seeing Venus against the disk of the sun from two different locations, right? You can triangulate again to find the distance. to find this triangle. The distance to the stars is measured in this way. Because the Earth moves, the stars show annual parallax. This Earth here on one side of its orbit. This is a nearby star seen against a background of more distant stars. 6 months in the future, the Earth is on the opposite side of the orbit, and now this star is seen in a different position. So if you observe the position of this star at this point of the orbit, this is how it's going to look, and then 6 months later, it shifted the position. In this case here, then, the baseline is the diameter of Earth's orbit. The parallax angle is defined as half of the shift of the star. This is important. It's not the full shift. The parallax is half of the shift. Notice that this immediately invites the definition of a unit of distance, which is the parsec. If you have that this is the baseline, so that would be 2 AU. The distance to the star given by this line is d, this black line that I just drew is d. And this is why you define the parallactic angle as half of the shift, because you want the baseline to be 1 AU. So this is the parallactic shift. Let's call it P. So the distance, d, is equal to 1 AU over the parallactic angle. We can then define the distance so that the annual parallax is 1 arcsecond. So this is called the parsec, which is a short for parallax arcsecond. Parsec. Thus, for parallaxes measured in arcseconds, the distances in parsecs are simply 1 over the parallax given in arcsecond by definition. This is the motion that the star would have against the background of distant stars as a function of the motion of the Earth. For a close-up star, you detect a big shift. For a more distant star, the shift is going to be small. The amount of the shift, the parallactic angle, is a measurement of the distance.